Now, as we get to things that are more complex, if you need to track your units as you go just to confirm,
Yeah.
then by all means, please track your units.
Right.
But there's a lot of things that we'll know ahead of time. If we're dealing with international standard units in the problem, then I can pretty much guess what the units will be in the end.
Okay, thank you.
An exception is, there is a master set question for chapter 8, I think, the gravitational one, where I asked you to come up with the mass of the sun in straight units. And that's a case where you do need to keep track of your units. All right, let's throw in the context here as a segue into chapter 2. A ball is projected at an angle of 50 degrees and 40 meters per second. We are going to break that up into perpendicular components. I'm going to take part of that, and I want to figure out how far is that, or how much of that is horizontal, and how much of that is vertical. We are creating a right triangle here. This is a projectile motion problem, chapter 3. There is a reason why I am doing horizontal and vertical, and that relates to the direction of acceleration, which we will get to.
Is that meters per second?
It is.
Okay.
So we have something being thrown at somewhere's about 85 miles an hour. Or as projected, whatever. No, 85. Major league players don't do that.
It's a strong throw.
Not me. Guess we got an answer here. Sorry, right?
Right. What are we looking for?
The horizontal and vertical components for the other two legs. Yes.
Yeah. Or did I hit them backward?
Something. No. Good with that number there, but that's not the same thing. Oh, that's a B. I thought that was a 6. Okay.
B and N, a label,
Okay, yeah. Okay, units?
units. That's 40 what, meters?
Meters per second.
Meters per second.
Yeah.
No. Yes.
I think we're working on fools. The third person.
sign is, would be beautiful.
Well, tangent is opposite. Oh, I get it, okay, so this is, that's supposed to be, obviously, that's supposed to be signed.
But then it almost becomes a nine.
Yeah, that would be sign.
For a second.
And is this good? So that would be.
Yeah, maybe that angle, square, you know.
Should I switch it back to radian, or is it okay in degree?
Well, that's in degrees, so when you do the cosine of 50 degrees, you should be in degrees.
Okay.
Because presumably in your
I'm in
calculator, you're
degrees,
doing
yeah.
cosine 50,
Hmm.
or convert that 50 degrees to radians if you don't want to get out of radian mode.
So it's, I was just asking like if I'm not finding the degree of the
Angle.
of the angle, then it doesn't matter, like it can be in the degrees the whole time.
Yeah.
Okay.
Maybe.
I was wondering if I needed to change it to radian.
No, no. Oops, wrong units.
Ah, no.
Yep. All right.
Yeah, I'm working for him. I work like,
That's set up right.
so it was Monday, Thursday, Friday, Saturday. Then I work 5 to 9. 12 to 8. Just,
I usually got so bad about saying I would be until like, yeah, I think you're in radian mode, I would be on there until like about 5 p.m. And then go home, sleep. And then
So it has to be,
just
Do
kind
you want
of.
to use
has to be in the right
Oh,
mode.
Do you want to use the calculator?
That's we started with degrees.
In terms of calculators, a number of you are using phones. There's nothing inherently wrong with you using a phone. It has come up on a test that there was a student who was using his phone for more than just a calculator. He lasted one more day in the class. If you need to borrow a calculator, I know there's one extra one here, if you know how to use a reverse Polish notation, I have one here. But we do have extra calculators if it comes to that on test or quizzes. So, but I'm not necessarily opposed to using a phone, but at some point I might step in and go, no more phones. I hope it doesn't come to that. All right. I think I just erased the problem. All right, so let's go back to the problem. So what we're given here is this is 40 meters per second, and that is 50 degrees. Some of you had already jumped to the chase. To find the opposite side here, in essence, when I found B over here, it's the hypotenuse times the sine, and it was the hypotenuse times the cosine. I don't have to set it up in this formal way. I can skip that step, and this is going to be the hypotenuse times the cosine of the angle, and the hypotenuse times the sine of the angle. Something else that might be advisable in some cases is I feel confident enough with the math that feeling confident enough with the math that I don't feel a need to draw it to scale. But sometimes it's really helpful to have some idea whether it makes any sense or not if we actually try to draw it. I know that's a 90-degree angle, 45 is half of that, 50 should be a little bit more. So if I imagine 45 splits it right down the middle, so I've got a 50-degree angle there. Those are 4 even segments, 40 meters per second. And then breaking it up, it should have at least some sense. And it looks like a little bit less than 30 there, or somewhere around 30. And then the other one, well, it should be longer. And this ends up being, my fingers were off here, but this was 25 point something
771.
meters per second. And this was 30.6 meters per second. And if you don't have your calculator, please make sure you can know how to reproduce these. All right, questions to hear?
Okay, I actually do.
Okay.
So are we assuming that, given the ball is thrown, no, wait, never mind, this is meters per second. I was thinking in just distance.
Oh. Go ahead, take it out.
I read your mind.
Excellent.
Yeah.
Good thing I just erased it. If you do try to draw it somewhat to scale, I mean, it was a really crude estimate, I was more off on the horizontal than the vertical. At least that way, if I'd been in radian mode, and I assume that was ultimately the issue, that if I'd been in radian mode on the calculator, I would have come out with way far off on that one, and that would have been a big clue that something was amiss. All right, so now, we're ready to do a little bit more formal stuff on vectors. Vector math is a little bit different than the math that most of you have done. For those of you who've had physics before, you've seen it. What kind of math have you been doing since kindergarten?
Like addition, subtraction. Addition and subtraction.
Yeah, what is that called? What kind of?
Arithmetic?
We're gonna do addition and subtraction here too, but they're not, you weren't dealing with vectors, I assume.
It's called scalar.
Indeed it is. Scalars. I'm assuming that your elementary school teachers did not use the term scalar, because I didn't have any of you when I taught elementary school. I made sure I used the word scalar for them. Just so that when they took physics later on, they could go, I've known about that for 10 years. Scalar math is what you have been doing. Vectors is what we are going to be doing quite a bit. We'll be doing scalars as we go also, but vectors become incredibly important here. And knowing whether something is represented by a vector or a scalar also becomes critical in a lot of parts of this course. So, for those who've dealt with vectors before, actually, oh no,
Yeah, we're like out of time.
we don't mind hanging out an extra 15 minutes, right?
I can't.
Except for Ray, he doesn't need you to know this stuff.
I'm a good guesser.
Hopefully I'll remember to do the first thing on Monday, so I'm gonna do it slightly differently. I want to give you an example of vector math. So, scalar math, first off, 2 plus 3 equals 5. If that is a shock to you, we probably should talk after this. But if I'm dealing with vectors, that is basically what we were just doing over there with the right triangles. If I take something that is 2 meters to the right and 3 meters up, those are 2 different vectors here, and they need to take the direction into account. So if I go 2 meters to the right, and I go 3 meters up, this is how you add vectors graphically, at least. This is known as the head to tail method. And even though this is the context of directions, and I think most people can understand, well, if I go 2 meters this way, and then I go 3 meters that way, you can physically, hopefully you can physically picture this. Where are you relative to where you started? Well, how far are you away from where you started?
So hypotenuse to it.
Yep.
Square root of 13?
But that's the distance you travel.
Finish it up.
Sorry, meters. Okay.
And the meters does not go under the radical. All right, so we have square root of 13 meters away, whatever that happens to be. 3 point something. And at what angle? Well, we just went through that. Our original numbers are 3 and 2, but we do a square root of 13, but let's do an arctangent of, let's label this cleverly, theta. Arctangent of theta, no, that's horrible. Theta is equal to the arctangent of 3 over 2. Which is 70 degrees. What is it?
56.6, sorry, 56.3 degrees.
Okay.
Sorry. that's okay.
56.3 degrees. Now notice the two key things that we have here, sort of wrapping up. Our final answer has a length to it, and it has a direction. So next time we'll talk about sort of converting back and forth between the two, what's known as rectangular form and polar form. We'll bring in the unit vectors I hat, j hat. I do not use x hat, y hat. For those who've done physics before, I do I hat, j hat, and I'll explain then why I do it that way. And for those of you who don't know what I'm talking about, what's the reason to come back next week? And it's also that cliffhanger that keep you wondering all weekend long. In case you've gotten over who shot JR, which probably only one of you understands the reference for. You understand JR reference? All right, cool. I'm good.
Now I can figure out our numbers.
Okay, so.